Morning. Alright, I guess we got enough people, so we'll go and get started. Alright, so let's see. So just the only real announcement I have is quiz 12. Opens up next Monday and closes on the following Tuesday and covers lessons 30 and 31. So that's all I really had to say on that. And keep in mind, this is the last quiz of the semester, so just keep that in mind while you're doing your studying. Okay, and and I also have Zoom office hours tonight. I'll put that there. Zoom office hours tonight, 6 to 7 p.m. All right, so that out of the way. Any questions on the homework? Anything you want to talk about, etc.? All right, cool. So let's go ahead and talk about the fundamental theorem of calculus, or at least the first part of it. So, excuse me. So, if we have, let's recall the following things. So, if we have that the capital F prime of x equals little f of x, then recall that we can express this as the integral of f of x dx. Should probably write on that. Dx equals capital F of x plus c. So keep in mind, this was the indefinite integral. Okay. So that was the indefinite integral stuff that we talked about way back in lessons 27, 28. Okay? But now the definite integral that we talked about the last couple lessons with the integral from a to b of f of x dx, remember that gives the signed area under f of x on a comma b. Okay? So you might think, alright, well that's cool and all, but what's the point? So what you'll notice is that both of these have some type of integral to them. So you might think, okay, well is there any way to combine these two concepts together? Well, the good news is, yes there is. So any way to connect these concepts? And the answer is, yes there is. Okay? And that's where the fundamental theorem of calculus comes into play. So if we have that, the antiderivative slash integral of f of x is capital F of x plus c, and f of x is continuous on a comma b, then the integral, the definite integral rather, from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay? So that's the fundamental theorem of calculus we've sort of been building up to regarding all the stuff that we've seen so far on antiderivative stuff. Okay? So that's that part. So now that we know what the fundamental theorem of calculus is, let's actually apply it. So for example 1, we have to evaluate the following definite integrals using the fundamental theorem of calculus. So the first one is, we're going to start with the integral from -1 to positive 2 of x dx. So first off, based off of the fundamental theorem of calculus, well, we should probably start by figuring out the antiderivative of x. So the antiderivative of x dx, so do you guys recall what is the general antiderivative of x? We're just focusing on the indefinite integral though.
X squared over 2.
Yep, it's x squared over 2
Plus c.
there, plus c. Good. Because remember, here we're just applying the antiderivative power rule, is all we're doing. Antiderivative power group. Okay? So with this lesson, you need to make sure you remember your general antiderivative rules with this. So just keep that in mind. Okay? So here's what that says. So the integral from -1 to +2 of x dx, we can rewrite this as, well, we're going to use bracket notation here. So we have x squared over 2 plus c. And then -1 to 2. So what this bracket notation says is that this means the fundamental theorem of calculus, so I'll abbreviate this as FTC for short, will be applied. Okay. So here's what that means. So if we apply the fundamental theorem of calculus, what that says is that, all right, so in this case, our bounds are a equals -1 and b equals +2. So since the general antiderivative of x is this guy right here, what this says is that we have to let x equal 2 in here, as per this part. So we have 2 squared over 2 plus c. And then we have to subtract that with the antiderivative value at a equals -1. So we have -1 quantity squared over 2 plus c. Okay? So here's what you notice with this. So if we go ahead and simplify all this as much as we can, well, what numeric value do we end up with here? We get 3/2, right? Because what you notice is that, well, wait a minute, we have a plus c and a plus c here that are going to end up being subtracted. So these go away. So all we're really left with is 2 squared over 2, which is, well, 2. And then minus -1 quantity squared, which is 1 over 2, so minus 1/2. So we end up with 3/2 as your final answer. Okay, so using the fundamental theorem of calculus, this is what we end up with as our final answer. So one thing to keep in mind with these types of problems is that, as I mentioned already, well, you notice that the plus c already went away. So plus c cancels out here. And you realize that no matter what antiderivative / fundamental theorem of calculus application you utilize, the plus c will always go away. So don't need plus c with definite integrals / fundamental theorem of calculus. Just one nice thing to keep in mind to make your computations a bit easier. Okay? So that's good and all. So now that we have that, and utilizing the methods from lesson 30, let's go ahead and check this with geometry just to make sure everything matches up as it should. So we're going to check with geometry. Okay? So what I mean by this is that if we take this region here, so here's our xy plane as usual. So we have x here, we got y here. So in this case, our function is just x, so we just end up with a straight line that passes through the origin. So what you'll notice from this is that, well, our bounds are from -1 to +2. So in this case, since f of x equals x, then what you'll notice is that, all right, we have this triangle here, and then this triangle here we have to add up. At least there's signed areas we have to add up. So in this case, if we have f of x equals x, so this is negative 1, 1, and 2. Then what you realize is that, all right, well, the area of this part, or I guess the side area, is equal to what? What area will that have, do you think?
1/2.
Well, that's the area, but now because it's below the x-axis,
Negative 1.
-1/2. Good. Because remember, because this is f of x equals x, that means that this point here is at -1 comma -1. So because of that, we have width 1 and then height 1. So we have 1/2 times width times the base, which is 1, times the height, which is again 1. But then because of the fact that we're below the x-axis, we have to multiply that by -1. So we have -1/2 here. Okay? So then, in a similar fashion, what would the area of this larger triangle above the x-axis equal? What area does that have? Yeah, it's 2, right? Because in this case, with this point here being 2 comma 2, that tells us that we have 1/2 times the base, which has length 2, times the height, which is again length 2. So we have 2 here. So the total area ends up being 2 plus -1/2 from this part here. So we get 3/2 as we got with the fundamental theorem of calculus. Okay. So just a nice quick little application from what we've talked about already. So any questions on any of that? Okay. So give you guys a second to write that down and we'll go and continue on. Good? Cool. All right, so the next application of the fundamental theorem of calculus will end up being the integral from pi over 3 to 2 pi over 3 of 6 times cotangent of x times sine of x plus 4 dx. So the thing is that with this integral, well, we have to take a look at our integral, well, our function inside the integral and see, is there a nice antiderivative for each one? So the first term, well, that has a pretty nice we look at this second term rather. The antiderivative of this part should be pretty easy to see. So the antiderivative of 4 with respect to x should equal what?
4x.
Yeah, just 4x, right? And again, because we're ultimately going to focus on definite integrals here, we don't need the plus c here. But now, what about this first term? Is there a nice antiderivative for this? Doesn't really seem like there is one, is there? But here's what we do know. If we take a look at cotangent times sine, is there any way we can simplify this down a bit?
Is it cotangent cosine over sine?
Yes, because, yeah, so cotangent by definition is cosine of x divided by sine of x. Okay? So what that tells us is that, all right, that means that this first term here equals, so we have pi over 3 to 2 pi over 3. So ultimately we have 6 times, so using this definition here, we can pretty quickly see that cotangent times sine should be cosine. So we have 6 times cosine of x plus 4 dx. And now this has a nice antiderivative now, doesn't it? So we have the antiderivative of 6 cosine of x dx should equal what? So one way to think of this, if you guys forget, is to remember, sort of work backwards. So remember, what function should we end up with so that its derivative equals 6 times cosine?
Sine.
Sine. Yeah, 6 times sine. So Okay, so that's that part. Good. So because of that reasoning, that should tell you, all right, the antiderivative in this case is going to be, well, 6 times sine of x from this part here, and then plus whatever the antiderivative of 4 is, which is 4x here. So that's our antiderivative that we'll need here. Okay? So we have pi over 3, and then pi over 3 to 2 pi over 3. Remember, just to indicate that we're, again, applying the fundamental theorem of calculus. So now we say, all right, well, now we let x equal 2 pi over 3 first off. So we have 6 times sine of 2 pi over 3 minus, plus 4 times 2 pi over 3. Okay. And then we subtract this function value here if we let x equal pi over 3. So we have 6 times sine of pi over 3 plus 4 times pi over 3. Okay? So here's what happens with this. So we have 6 times sine of 2 pi over 3, but what exact value does that take here, if you guys remember your unit circle? So as I remember the sine of 2 pi over 3 from the unit circle. Root 3 over 2, right? So we have root 3 over 2 here, and then we still have, well, in this case we have 4 times 2 pi over 3, so that's going to end up being 8 pi over 3. And then here we have 6 times sine of pi over 3. So if you use a unit circle again, what's the sine of pi over 3? Okay. Yeah, root 2 over again. Yeah, so root 3 over 2 again. And then plus 4 pi over 3. Okay? So what you'll notice is that, oh, wait a minute. Well, these two terms, if we subtract them, those are going to cancel each other out. So ultimately, we're just left with 8 pi over 3 minus 4 pi over 3. So that should pretty quickly simplify to, if you subtract these two together, you should be able to get 4 pi over 3 out of this. Okay? So that is part B. So, any questions on that? Alright. Okay, so now 2. So, example 2. So, the goal of this is to find the area enclosed by the graphs of the following equations. So we have y equals 6 times the square root of x minus x quantity squared, y equals 0, x equals 1, and x equals 4. Okay? So here's a couple of things to keep in mind with these kinds of problems. So if you'll see a problem like this on the homework, what you'll notice is that, well, if we take 6 times square root of x minus x quantity squared, what you'll notice is that, well, this quantity, no matter what happens, because of the squared here, you're always going to end up with something that's non-negative. Okay? And this will usually end up being the case of problems that you deal with on the homework. Okay? So we have this as non-negative, and then remember, y equaling 0, that directly corresponds to the x-axis. Okay? So because of that reasoning, what that tells us is that, so we have to evaluate integral below to get area. Okay? So because of that, since we're saying we have this function above the x-axis, and we're measuring against the x, and then one of our bounds is again the x-axis. So we have this function from x equals 1 to x equals 4. That does this thing, whatever, up here. But then because of the fact that one of our bounds is the x-axis, that tells us, all right, that means we're essentially trying to figure out this area here. So again, this is the x-axis. We have x equals 1 here and x equals 4 here. And then this, the top curve here is just this guy right here. Okay? So because of that, that should tell you, all right, based off of the applications we've been seeing on the definite integral, that means the area A should be, let's see, it's going to be the integral of, well, you're going to have this quantity 6 times the square root of x minus x quantity squared inside the integral. And then your bounds are going to end up being what? So what would our bounds here and here be?
1 and 4.
Yeah, so 1 and 4, right? Okay, so basically now it says, all right, if I want to figure out what this area is for solve the problem, all I got to do is evaluate this integral. Okay, no problem. So let's do that. So in this case, before we try and work with this, you'll notice it's not really this function here by itself, as it currently stands. Well, it's not really a nice integral to try and differentiate on its own. So at this point, we say, all right, well, we have a squared here, so that should be a pretty good indication we got to expand stuff out at this point. So if we do that, we have the integral from 1 to 4 of 6 times what? So if we expand out this part right here, just the root x minus x quantity squared portion, what should we end up with as our expanded out expression? Good.
Is it x squared minus 2x root x plus x?
Yep. So 2x root x, and then what was it?
Plus x.
Yeah, plus.
Squared. Oh, just plus x. Okay.
Yeah, plus x, right? Because remember, in this case, this is just square root of x quantity squared, but that's just x. So, okay. So what you'll notice is that, all right, so we have that, which is good. So we have the integral from 1 to 4. So if we now distribute the 6 in, we have 6x squared minus 12 times, well, let's see, we have x times the square root of x. So combining those gets you x to the what power? 3 halves, good. Remember, just using our good old exponential properties. And then plus 6x here, dx. Okay? So now, at this point, we have to use our antiderivative power rule a bit more often now. So since now things are getting slightly more complicated, I'll go ahead and recall the antiderivative power rule for you here. So we have, it was x to the n dx equals x to the n plus 1 over n plus 1. And then, even though we do normally incorporate plus c, we don't technically need it here because of the thing we talked about in example 1. And keep in mind, this is for n not equal to negative 1. So if we utilize this antiderivative power rule here, then what should we end up with as our antiderivative of this whole thing? Go ahead.
Is it 2x cubed minus 24 over 5x to the 5 halves plus 3x squared?
Yep. So we have, yeah, so actually why don't I do this? So why don't I just do an extra step just that way we all know what's happening. So yeah, you mean your antiderivative is correct, but I just want to make sure that we're all on the same page on this. So what we have is 6 times, well, let's see, x cubed over 3 minus 12 times x to the 5 halves over 5 halves and then plus 6 times x squared over 2 from 1 to 4. Okay? So, like you said, that simplifies to, in this case, 2x cubed minus 24 over 5, x to the 5 halves, and then plus 3x squared, and that's your antiderivative. Okay? So now if we apply the fundamental theorem of calculus, well, let's see what we get out of this. So we have 2 times, so in this case we first let x equal 4, so we have 4 times quantity cubed, minus 24 over 5 times 4 to the 5 halves, and then plus 3 times 4 squared. Okay. So that's the first part of our fundamental theorem application. The second part says, all right, now you have to subtract that with this same function evaluated at x equals 1. So we have 2 times 1 cubed minus 24 over 5 times 1 to the 5 halves, and then plus 3 times 1 squared. Okay. So now, here's where things get a little more interesting. So let's see. What's happening here? So if we evaluate this all into a calculator, well, let's see. So what we have here is 2 times, 4 quantity cubed. So if we plug all this into a calculator, so term by term we get what? So 2 times 4 cubed will be what? 128. And then as a fraction, this term here becomes what?
768 over 5.
768 over 5. And then plus 48. Good. Okay. And then minus, 2 times 1 cubed, that's just 2, minus 24 fifths times 1 to the 5 halves, that's just 24 fifths, plus 3 times 1 squared, so just 3. All right. So now what we end up with is, we have 128 minus 768 over 5, plus 48, then minus 2 plus 24 over 5, minus 3. So then now we just combine everything, clean everything up. So we have, if we add all these whole numbers together, add, subtract as necessary, we end up with 171. And then adding the terms with the over 5 factor, we have minus 744 over 5. And then that's just, if you put this in, either put this into a calculator or do a quick little bit of math, you should end up with 111 over 5. And that's your final answer. Okay? So that's example 2. So just be aware that problems on the homework can involve quite a bit of algebra, so just a bit of a heads up on that front. All right? So any questions on that part? All right? So at this point, I just have one more quick example for you guys to do, so I'll let you go ahead and take a look at that. So basically, this example says evaluate this definite integral from 1 to 2 of x cubed plus 1 over x squared. Okay? So I'll give you guys about 5 or so minutes, or however long it takes for you guys to do this problem, and then we'll go ahead and reconvene in 5 minutes. And you guys can take off super early. And if you need a hint, try simplifying this expression first. So, give you guys about 1 more minute. Okay, let's go ahead and reconvene. So, for those that got a numeric value, what did you end up getting? That's not quite what I got. Did anyone else get another value?
I got 2.
I got 2 as well. So, yeah, let's go ahead and talk about that. So, first off, if we take a look at the integral from 1 to 2 of x cubed plus 1 over x squared dx. And we say, all right, well, if we break this off, we have the integral from 1 to 2 of x cubed over x squared plus 1 over x squared dx. So if you clean that up a little bit, you should end up with, well, the integral from 1 to 2 of, that should just be x for the first term. And then the second term can be rewritten as x to the negative second to be able to apply the antiderivative power rule. So in doing so, you should be able to get that the antiderivative of this is, well, x squared over 2 minus x to the negative first from 1 to 2. Or if you prefer, you can rewrite this as x squared over 2 minus 1 over x from 1 to 2. So once we apply the fundamental theorem of calculus, we can say, all right, well, like we said, let x equal 2 in this guy right here. So we have 2 squared over 2 minus 1/2. Then minus, now we do the same thing, except now we have x equal 1. So we have 1 squared over 2 minus, well, essentially 1 now, because we have 1 over 1. So now what happens is that if we go ahead and clean everything up and then distribute the negative, we have, let's see, 2 squared over 2 just becomes 2, then minus 1/2. And then we distribute this negative, so we get minus 1/2 plus 1. So what that tells us is that, all right, well, we have 2 minus 1/2 minus 1/2, so that becomes 2 minus 1 plus 1, or just 2. Okay, so any questions on any of that? Okay, well, that's all I really have for today. So you guys get to go. You guys get to get out early, a whole 12 minutes. So, yeah. Enjoy your weekend. Enjoy your Friday. I'll see you all in the last in-person lecture on Monday.